Okay, so we are recording. So last class we discussed the Bandits algorithm, right? So we discussed that there was this. We'll do some analysis of the algorithm today and also do another way to sample next actions. So we said that there are like k arms of this casino game, and you just pull one of them and try to see which of the arm is most profitable to you. And we saw that the function that was used to draw the arms was the expected reward. So all the participant, everything that the agent or the person is wanting to do is maximize the expected reward at a given time. That's all we had seen. And from that, we saw that using the law of large numbers, we approximated this expectation every time the action was A using the Monte Carlo sum. So this is we have proved that using weak law of large numbers that the variance of this sum goes to 0, and the that is the sample expectation goes to, so this goes to the expected reward to the actual expectation as n tends to infinity. This was the weak law of large numbers. We had seen this. So and then we came up with this approximation algorithm, that an online approximation algorithm. Say we take, so choose a reward, sorry, choose an action A, and your Q function for that function A is updated as this exponential average. So this is how we saw that this equation turned out to be. Very simple, just rewriting the equation, we see that this is what it turns out to be. The expected the equation of the sample mean turns out to be this. Okay, so where yesterday, last time I told you this was equal to 1 by n plus 1, which we found out from the from solving the equations. So, but today I'll be telling you, you can choose an arbitrary alpha, which is called the learning rate of the equation, which has a particular few characteristics. So let us look at those characteristics one by one. And before we go into the alpha n's, I'll try to give you a intuition for what this equation actually symbolizes. Sorry. So what this update equation actually means. So to do this, we'll be using basic differential equations from, and we'll be using a stochastic version of it. But let us try to understand a numerical approximation technique of a differential equation. So it's a little detour. Bear with me. So it'll be useful for you in other things as well. But we'll do a few mathematical stuff today. We'll try to understand what is called the Euler method, and we'll also try to see the gradient descent. So two things, what Newton from Newtonian calculus is what we'll try to do. So what this actually says is, say you have a differential equation. This is an ordinary differential equation, because we only have full derivatives, no partial derivatives here. Ordinary differential equation such that the derivative is equal to the function f of x comma y. So it is some implicit. So here y is mapped to some gx by some implicit function. So this is an implicit function. The idea is you cannot separate x and y, but y is a function of x here. So it's not on the entire xy plane, but it's a curve. It can be any curve where there is an implicit match between y and x. But we do not know how to solve this differential equation. Say you do not know how to separate the variables, you do not know exponential methods to solve differential equations here. So there's no way you can solve it. So where what you can do to actually visualize and characterize the dynamics of this equation is use what is called the Euler's method. So what is an Euler's method? Let's try to understand that. Say this function is f of x comma y, not this function, sorry. So at this point, this point xn, you have, say, a particular yn. That is, by this implicit mapping, yn is equal to g of xn. But we do not know what the implicit map is. All we know is we know the starting point xn comma yn, and we know. So do you agree that this is the derivative of this function at this point, the tangent at this point? So this is dy. Do you agree this is dy dx, which is given to us? This is given, right? Any questions? So at this point, this will be at xn comma yn. This is equal to f of xn comma yn. Do you agree? Is the derivative at this point? Any questions? Okay, seems very easy to all of you. Now, if you see, the tangent actually always approximates the graph or the curve if your step size h is small enough. So if you know this tangent, this is theta, right? So what is the height that you will get? Can you tell me? So let us look at this triangle in a better way. So this is xn. This is xn plus h. This distance is h. So this is theta. So such that tan theta is equal to f of xn comma yn. So what is height? What is this height that you will get? Capital H. Just h tan theta, right? Or sorry. Yes. Right. So h is equal to h small h tan theta. Yes or no? Correct. Which is nothing but equal to the derivative at that point. We can write dy dx as well at xn comma yn. This is f of xn comma yn. Do you agree? Any questions? So this is the point that we call as yn plus 1. So this is your new data point xn. So this is, I'm trying to say is, I'm trying to move on the curve. So what I'm trying to do is say, I'm drawing a cartoon version of it. So if this was your xn, comma yn, I approximate this graph by xn plus 1 and yn plus 1. Do you agree? When h is small enough, this will be the trajectory of the curve. Yes or no? That's how the derivative is defined, right? So all you can say is dy dx is f of xn plus h minus f of xn by, sorry, you can write this as g. Sorry, g is the implicit map. So let us write this as yn plus 1 minus yn by the xn plus 1 minus xn. Yes or no? I can write this as at xn comma yn. This is the derivative, how it is defined. So in your school, you wrote this as xn plus h and g of xn, right? Where limit h tends to 0. Yes or no? Any questions? Okay. So what I can write this as is, what is the denominator if you've understood? Xn my plus 1 minus xn?
H.
That is h. So if you multiplied h on the left side, so the left side, the derivative is already given you in as a function of x comma y. X comma yn is equal to yn plus 1 minus yn. So the update equation, the algorithm becomes the Euler's algorithm for solution to a differential equation. Only this is analytical solution, not this is only a graphical solution, not a closed form analytical solution. So this is you repeat, say you start from x0 comma y0 and you repeat. Can you tell me what will I repeat? How will I repeat the trajectory? Xn plus 1 as xn plus h and yn plus 1 as yn plus f of xn comma yn into h. Is this fine with everyone? This is also if essentially the Taylor's equation. We'll see why is the Taylor series as well. So is this fine? Any questions? So why did I tell that? So what I meant was, so this is the equation. So for every y, you can write the next step as yn plus 1 as yn plus a small delta step size into the function. Do you see a similarity between this and the equation that you have? Yes or no? You see a similarity or not? So let's write it down once again. So this essentially means dy dx is equal to f of x comma y. Now, in the Bandits algorithm, what is given to you? Qn plus 1 is given as Qn plus alpha n plus 1 into Rn plus 1 minus Qn. Yes or no? This is what is given as in the Bandits algorithm, right? I just recopied it. So what do you see a similarity between this and the Euler equation? So can I write it in terms of a differential equation? So that's what I'm trying to write. I'm trying to write the Bandits in terms of a differential equation. It will help me analyze the equation better. Anyone? What can I do? N plus 1 minus Qn by alpha n plus 1 is equal to Rn plus 1 minus Qn. Yes or no? Correct? If step sizes are small, that is alpha n plus 1 tends to 0. What can you write the left hand side to be? Difference by the what can you write this as? Delta x, delta y by delta x. That's the derivative, right? So we'll replace let t be analogous to n at a particular time. So you can write dq dt is equal to RT. So RT and RT plus 1 are the same because it's a continuous system that we are trying to plot. So they don't make a difference at all. This fine with all of you as h tends to 0. This is what I'm trying to write. This is the analogous differential equation. Right? And why did I write this? So let us try to understand why did I write this. So now I got the ODE. Now we'll try to interpret this for the convergence of the algorithm. So I'm still waiting for questions. If you don't have questions, I'll just go.
So why did it become dqt by dt actually when it's let t equal to n, then alpha n plus 1, how can it is t?
So that's the step size, right? So the update that you're writing here,
Yes.
the function that I wrote over here, dy dx, we wrote yn plus 1 minus yn by xn plus 1 by xn minus xn, right? Yes or no?
Yes, yes.
So I am saying alpha n plus 1 is xn plus 1 minus xn. Yes or no? Or tn plus 1 minus tn. Right? This is the step size that I'm taking. So this is exactly, so what I'm trying to say is this is exactly this Euler equation. Yes or no? The right hand side that I have written. So that's why I directly could write this as this equation. So t plus 1 is actually tends, so tn plus 1 tends to tn. So therefore we take it to be a continuous time signal. So if it is continuous time, tn plus 1 and tn does not make sense because they are not indexed at t. So t is continuous here. So why am I writing this? It will be clear just now. So now this is this equation that I got. So but that rings a bell. Does it ring a bell? Why do I say that? So which of in this equation, sorry, not n, so it will be t, q of t, because we are replacing n as t. Just recall. Fine. So now here we are saying that, do you agree that RT is the only stochastic noise, or the random noise is only random noise? Yes or no? RT is random. These two are still, these two are, QT is a fixed function. Yes or no? Because
Yes.
QT is defined as an expectation, which is fixed. Expectation of RT given AT equal given AT. This is a fixed function. But we see that RT is a random noise. Every time you sample a arm of the multi-armed bandit, what ends up happening is you get a random noise from a distribution, like we saw a uniform or a normal distribution last time. So we cannot really deal with this. This becomes a stochastic differential equation because RT is stochastic. So to convert it into a normal differential equation, so I'm being a bit hand wavy uh, to aid UG students, but yeah, it will be a bit not very rigorous, because if it is very rigorous, we need to derive a lot of things from the stochastic differential equation literature as well. So we'll not do that. So what I'll try to do is I'll try to intuit what I'm trying to what can make this an ordinary differential equation. I will add expected value of RT and subtract expected value of RT from this equation. Okay. So where is it? Yeah. Minus RT minus QT. Okay. So this is what we're going to do. I'm going to add expected value of R. Is this fine? Looks like fine. Yeah. So I'm going to add expected value of RT and subtract expected value of RT from this equation. So what do I get? I get E of RT minus RT, and I get plus, am I making a mistake?
Yes, the RT would have been positive.
Yeah. Correct. That's what I'm thinking. Correct. Thank you. This is positive. So I get RT minus expected value of RT, and I get expected value of RT minus Q of T. Yes or no? This is what I get. So now look at this term. This term is called a martingale. But we'll not go into what is a martingale, but it's called a martingale, where RT minus expected value of RT. Can you tell me what will it tend to in expectation? What will be the expected value of this? If by linearity of expectation, we have discussed linearity of expectation. This will be the expected value of RT minus expected value of RT, which is again this is a constant, so it can come out. So this is 0, right?
Yes.
So what by law of large numbers, what happens is by law of large numbers, as t tends to infinity, this term goes to 0. This goes to 0. The martingale MT goes to 0. Right? And when the martingale goes to 0, we can just ignore this. So this equation at t, limit t tends to infinity, becomes expected value of RT minus QT. Okay? Because this term, the martingale goes to 0, that we saw in expectation. Goes to 0 in expectation. This is why it's called a noise. This is a noise term, and this is the constant, this is the function term, and this is the noise term. So the noise, as you get more and more samples, as we have seen before, goes to 0. Okay. So now what can you say from this equation? Why did I do all this lot of hazard to come up with this differential equation? That is, the first order derivative of q is expected value of RT minus the QT function. So because I did it, because if I set it to 0, which is the optimal value of the function, optimality, at optimality, q star t is 0, it's also called an attractor. We know that when the function is optimal, the derivative is 0. Where what happens? This is equal to expected value of RT minus QT, which means QT is equal to expected value, or the optimal QT star is the expected value of RT. This is what we as limit t tends to infinity. Clear with everyone? I said last time that this is what we are trying to map, that we are trying to find out the expected value of the function, of the reward function, and we see using the ODEs. Using ODE, we see indeed, as t tends to infinity, QT tends to expected value of RT. That's all we wanted, right? This was the algorithm that we wanted to find using the sample updates. So we started, so again, recall, we started all the way from the sample updates and showed that even with the sample updates, we can converge to the expected value of the actual expected value. Is this fine with everybody? Any questions? It's actually very simple, but if you have any foundational questions, please ask. Anything? Okay. So now I'll tell you a few properties of this before we go into other sampling methods. Okay, discuss this. So now the next property that we'll be discussing is, this is the property. So if you are following, what can alpha n plus 1 be, or alpha n's be, is the question. So we saw one of the alpha n's was equal to 1 by n plus 1, right? This is the equation that we had got for the, so for in, let me write it down if you are confused. Alpha n plus 1, Rn plus 1 minus Qn, right? So my question to you is, what the values of alpha will guarantee convergence? So there is a popular algorithm in stochastic approximation, which is called the Robinson-Munro algorithm. Munro algorithm, or Robinson-Munro conditions, which says that this algorithm converges. So you remember this algorithm is essentially equal to dq dt RT minus QT, or rather expected value of RT minus QT, plus the noise, the empty term. This was your equation. But what the Robinson-Munro algorithm says, that it converges, that is, this goes to 0 and this converges to QT if alpha n plus 1s are all greater than 0 for all I, for all n. Let's not put n plus 1 anymore. Number 2, summation of alpha n is equal to 1 to infinity, or 0 to infinity, whatever you want. This is equal to infinity. I'm not going to the proof of this, it's very complicated. We need a lot of convergence results in probability to understand this proof. But these three conditions must be met. The Robin-Munro condition, which is the summation, and the square of alpha n's will be less than infinity. These are the three conditions. If they are met, then this algorithm converges. This converges. But I'll give you an idea why this is done. So why is this to infinity? Because we want the effect of every reward. And this is less than infinity because we want to mitigate noise. So you can show in the proof that the second order terms are related to noise. And the first order terms are related to rewards. So this is what you can show, but that's not our concern. You just have to remember that the alpha n's must be summing to infinity because we want all the rewards. Since it's related to the rewards, we want all the rewards to be a part of our Q function. And since the second order terms are the part of noise, we want them to go to 0. That's the two things we must keep in mind. But let's take a few examples. So I'll do one example for you, and the second example will be a homework. Please upload this. It's going to be a fun exercise. N plus 2 for n greater than 0. N greater than 0 equal to 0. So this is your homework, the second one. It's a bit of a brain teaser, so I'm not doing it in class. It's there in most of your first year courses, convergence of sums and so on, real analysis. But it's fine. The first one we'll be doing. So we want to prove that alpha n equal to 1 by n plus 1 converges using the Robins-Munro algorithm, Munro conditions. Anyway, can you prove? First condition, do you agree alpha n is greater than 0? Because n is greater than 0. These two conditions are met. Second condition is summation of 1 by n plus 1, n equal to 0 to infinity. Is it infinity? Is the question. So let us try and solve this. So it's an interesting question to solve. So I'll rewrite this equation as not an integral, sorry, 1 by n is equal to 1 to infinity. Okay. So what is this equation is the question. Does this converge or does it diverge to infinity is the question. So any idea how do we do this? Anybody in your first year, do you remember what did you do?
There's some tests,
It is
I think.
it is a tailored expansion of
Okay. So I'll give you a simpler method. No need of a Taylor expansion. Okay, you're telling Taylor expansion of an exponential?
no, I got it wrong.
Yeah, I think this is a very, very stereotypical proof. It's very interesting as well. So let us consider this function f of x as 1 by x, correct? So what do you agree? Do you agree that let us take the derivative of this function? This is 1 by x square, yes or no? This is less than 0. What does it say? It's a decreasing function. We all know that. We know how to plot this. It's a rectangular hyperbola. X greater than 0. Fine. So what does this mean is, say this is x is equal to 1. And this is x is equal to 2. Correct? What does this mean? Can I write this as 1 by 1? So this term at this is 1. At this will become 1 by 2. So this will become half. Why can I write this as this area? Just look at the area I am shading. This area. And this goes on decreasing. Please, please follow. This goes on decreasing. So this term becomes 1 by 1 into 1 plus 1 by 2 into 1 plus 1 by 3 into 1 and so on. Yes or no? Can I write this as this area? This is fine with everyone? Any questions? So do you agree that the integral of x dx from 1 to infinity is less than the summation of n equal to 1 to infinity? Why? Clearly, you can see that the area that is covered under the red curve is less than the green curve. Yes or no? So for any decreasing function, for a decreasing function, the integral is always a lower bound on the discrete sums, right? Yes or no? We proved this just now. Any questions? I'll not go ahead unless this is fine to everyone.
It's okay.
Yeah. So, so this integral we know is log x from 1 to infinity, which is log of infinity minus 0, which is infinity. So which says that our sum of interest is Sn is greater than infinity. So that is not possible, which means Sn is equal to infinity. So this sum is actually diverging. This is what I'm trying to say. This sum, where do you go? Where do you get the sum? Yeah, so this is also holds. Great. Number 3, equation of the number third part is 1 by n plus or alpha n squared, n equal to 0 to infinity is less than infinity. That is, it converges. Yeah. Now, anyone who can help me with this? This we cannot use the. Can we use the integral trick here? It's also a decreasing function. I will do the integral trick and ask you. Can I do this? Can I get something interesting out of this? So this term becomes 1 by n squared summation of n equal to 1 to infinity. So if I just write 1 by x squared dx, 1 to infinity, this is 1 by x minus, that is infinity to 1, because I change the sign, and that becomes 1. So is this correct? Does this say it's finite? I just did the integral. So it says that the summation of 1 by n square is greater than. So this is the logic that we have to use. We have seen that for a decreasing function, this integral is always less than the sum. So we clearly see that this integral is, where is it? Yeah. It says that this summation is greater than 1, n equal to 1 to infinity 1 by n square. Do you agree? But do we get any answer from this? This can still be infinity, right? If it is still infinity, it's greater than 1. This trick does not work. To get to it to be less than infinity, what do you think we need? We need an upper bound, right? This should be less than an upper bound C, not a lower bound. Any questions? Okay. So now how do I get an upper bound? Can you tell me? So 1 by n squared. First of all, let me write this. Do you agree n is greater than n minus 1 for all n greater than 1? Right? Right? Which means 1 by n minus 1 is greater than 1 by n. Fine. Which also means yes or no?
Yes. Now we are gonna use.
Okay. So I'll not sum from 1 to infinity, I'll sum from 2 to infinity because that's the condition. And is greater than summation of n equal to 2 to infinity 1 by n square. Now to get it to be equal to n equal to 1 to infinity, I will just add 1 on the left hand side. Yes or no? This is fine with everyone? This is okay? Okay. So now what can I write this sum as? Can you tell me? N equal to 2 to infinity 1 by n into n minus 1. This is
The
your
numerator, it will be n minus 1.
okay, yes, correct. So I can write this as n minus 1 minus 1 by n, right?
Yes, yes.
Any you were saying something regarding any
Yeah,
mistake that
that's
I made? Yeah,
no,
yeah.
no.
Correct.
Actually, that I was saying that.
You are saying this, okay. Okay. So this is the numerator I can write as you were saying, I can write this as n minus n minus 1. That's it. Very good. So now your class 11 and 12 summations. This all the only the first term and the last term remain. This is 1 by, let me write it down if you don't remember. 1 by 2 plus 1 by 2 minus 1 by 3 dot 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 dot. So this term, this term, this term, this term all gets cancelled, and you have the last term, that is 1 by infinity. That is 1 minus 1 by infinity. That is equal to 1. So this term becomes 1. So it says that summation of n equal to 1 to infinity 1 by n squared is less than 2, which is less than infinity. Hence proof. Fine. Any questions? So similarly, try and prove the second one. I'll give you a hint for this. The hint is, for this second one, hint is 1 by n is less than log n by n for n greater than e. Right? So it's greater than, you're just considering what am I saying? Yeah, this, right? Because log n is again greater than 1. This is the hint that you can use. And the second hint you can use is, that is also you can prove. I will, if you are showing interest, I will show the proof. I have it ready, but due to interest of time, I'm not doing it. N to the power alpha converges the sum of n to the power alpha for alpha greater than 1. These two are the hints that you can use. I think that can help you to solve the second alpha n as well. But this comes to, we come to an end of the Q-learning algorithm for bandits. So now, once we get that idea of bandits, what did we do? We assume that the action is selected now. But now, actually, this action selection and learning Q are going hand in hand, right? Yes or no? So we last time in class, we showed that using some epsilon greedy algorithm, we sampled the actions. Yes or no? But now I'm trying to formalize what these actions actually mean. So let's try to do that. Okay. So now what would be a good action to select? So first of all, recall what is Q of t or Q of n or Q of an action at time t? Can you tell me? That is the expected reward given you have chosen the action A. Yes or no? Correct? Any questions? Okay. In case you're not following or not, I'm not audible, please stop me. I just get a bit distracted when people are not talking. Okay. So now, which is the action? So I ask you this question, which action is the best action to select? If Q star Qt of A is optimal, which action is best to select? Can you tell me, anyone? These are the rewards. Which action is the best to select? The action with the, sorry?
Highest reward.
Yeah, go ahead.
The action with the highest reward.
Action with the highest reward. So if this was the optimal Q function, so one, so this reward, expected reward could be 1, this could be 2, this could be -3. I will select this action. So I will select, say this is 1, 2, 3. So I will select action 2. This is arg max of A belongs to A. Qt of A. This is the optimal action to select. Yes or no? This is the optimal strategy. Do you agree? But we showed that if we do that, what will happen all the time? So initially, but the problem with this is, can you tell me the problem with this? So you start, say the problem is something like this. So I'll just write it at the end. Problem with greedy action selection. Can you? So say Q0 at 0 for, we did say all zeros. We did it for 5 zeros last time, 5 actions, 5 hands are all zeros, right? So now I take an action A equal to 2 and Q1 becomes, say the reward that you get, reward is equal to 5. So what will be a Qn plus 1 or Q1? Can you tell me of 2? Alpha n plus 1. Let us take this as 1 by n plus 1, which is equal to 1 for n equal to 0. Reward is 5 and initially it was 0. So now tell me what would be the value of n2? What is nq of 2? The second action, this is 1, this is 2, this is 3, this is 4, this is 5. Tell me. This is 0, right? Initially.
Yes.
This is Q0 of 2, this is R1. Now this is 0, this is 0. So this becomes Q1 of 2 becomes 0 plus 5 equal to 5. Okay. I rewrite the equation. Do you see the problem now? Now next action I select. This was randomly selected because all were 0. All were 0. So randomly selected. So now what? Now if my condition is argmax of Qt of A of all actions, what will be this answer to this if t equal to 1? What is the maximum argmax means which index gives you the maximum, which action gives you the maximum? Tell me. Like in this array, 5 is the
5.
maximum. 5 is the maximum. 2 is the argument maximum. Right? At what values of A? Argument maximum means what values of A? Ask me if you are not comfortable with the notation. What values of A is Qt maximized? So do you agree this will be 2? Correct? Yes or no?
Yes.
So now every time you will be ending up selecting 2. Every time 2 will come. Will be sampled. Sampled unless expected reward becomes less than 0. So clearly there is a problem, right? So you are so greedy that you just went 1 and you did not explore. So the entire exploration strategy.
It's the difference between the greedy problem and a DP, when it in dynamic programming. What we did.
Yeah, exactly. So you'll be keeping on selecting the second action and you will not be ending up selecting the other actions. So to do that, what you will be doing is, we discussed last time, we coded it as well. We use an epsilon greedy strategy. That is, we selected epsilon with say we sample a random variable with Bernoulli epsilon probability. So if it is say 10%, so 10% of the times I will select a random action, and say 10% of the times I will select a random action. And 90% of the times my optimal action. But again, this is very heuristic. Epsilon is a hyperparameter, as I have mentioned over here, and can't be, and we don't, and also as t tends to infinity, what happens? T tends to infinity. What will happen? Anyone? Qt goes to Q star, right? We have seen this using the ODEs, differential equations. right? It is the optimal strategy. And now we have optimal strategy as t tends to t is very large. So why do you want to be very explorative? Like the idea is once you're very old enough, you already have a very good model of the world around you. So you try to exploit more often than try to explore. So this will always make you explore, which is generally not required in our case. So that it does not guarantee. So it keeps on exploring even with equal weightage as the time also increases. Any question? So in the code, you can check that number of non-optimals. So I'll give you a UCB code as well today. So I'll give you a homework on the code as well today. You can try it out where you can see that the number of times the optimal action is not selected in epsilon greedy is much more compared to UCB, which makes this our next algorithm be the star of the class today. This is the main topic of discussion. So I say that I learned. So first of all, remember nothing is going to change. I'm going to update Qn as alpha n plus 1 Rn min plus 1 minus Qn. I'm going to update the alphas like this as I was going to update. This is the update. But my action selection will not be just purely based on an epsilon greedy. My action selection will be would be argmax of A Qt of A plus some C into log of T by Nt of A. We will prove this. Why is it this? But let us try to have the intuition of this first. Any idea why am I doing this? So let us have T for the time being for easy notation. Just wait one moment. I'll just come back to the T plus 1. Okay, so this is your A T plus 1 is what I'm trying to say. So can you tell me I am going to select an action based on this strategy where I use the Qt of A of that action and I have some term over on the right. What does this term mean? So log T, very interesting term, this log T term. As T goes to infinity, what happens? So before even going to log T, which is there, let us first see NT of A. This is number of times an action A is selected, right? This is the number of times an action A was selected. Fine. Okay. So now as T tends to infinity, what will happen? First T tends to 0. Let us see. T is small, T equal to 0. What will happen? What will happen to log T by? If you want to put some delta T plus 1 on all, you can do that. So let's say NT of A equal to 0. What will happen to the term on the, what will happen to log T by NT plus A and delta? Delta tends to 0. This is for numerical stability. So it can be some numbers when we implement like 10 to the power minus 9 or something so that we don't divide by 0. Okay. Can you tell me what is this going to be? This is going to be infinity, right? Say T is small. Say 2 or 3. Right? This is going to be infinity, yes or no? Everyone? Because the denominator is tending to 0. Right? When T is small, every action, when T is small, NT of A is small too, which makes log T by NT of A go to be infinity, which means that only term 2 dominates, and same for all actions equal to infinity. So you select explore more. right? If it is same for all the actions, you end up exploring more. As t tends to infinity, what will happen? What happens to log t by t? This goes to 0, right? Log t decays, log t by t goes to 0. Yes or no? You can set the behavior t tends to infinity. Log t, you can do the L'Hopital rule. ddt of t, which is equal to 1 by t. Limit t tends to infinity, which is 0. Right? So what I'm trying to say is log t by t goes to 0, which means term 1 dominates. And qt or at plus 1 is just uniform or argmax of a qt of a, right? When large, when t is large. This is when t is small, at plus 1 is uniformly selected between action 1 to action n. Is this clear to everyone? So the idea is first explore, then exploit. Any questions? I will wait and then I'll go to the proof of this. It's very interesting proof, but any question? 1, 2. So first, this is the exploration stage. And this is the exploitation stage. Anything you want to ask? Is it clear to everyone? Am I audible?
Yes,
Yes.
Yes.
So now I'll try to do something, try to prove this. So how do I prove this? Say, first tell me what is your reward or what is your QT? Do you agree? QT is again by definition Ri, I equal to 1 to n. Yes or no? Or Q n of an action A, right? Action is equal to A every time. Do you agree? This is what we defined the Q value function as, the expected reward. Now what I say is, say Ri is distributed as normal 0, 1. So if it is not distributed as normal 0, 1, what will I end up doing? Can you tell me? I can still prove this using normal 0, 1. If it is not actually distributed as normal 0, 1, can you tell me how? If not, what can you do? You can normalize Ri minus mu by sigma, yes or no? This is how we saw. This is the law of large numbers that we saw. Central limit theorem, sorry. So any equation, so I sampled from the uniform in the previous class and showed that if we normalize, that is subtract the mean and divide by variance, divide by standard deviation, this becomes normal 0, 1. So there is no problem to convert it into normal 0, 1. So we can safely assume it to be normal 0, 1. Fine. So now tell me what would be the distribution of Qn? What would be Qn distributed as? First tell me. So I will tell you it is distributed as a normal again. This is a homework for you if you really are wanting to know why is this. So 2024 Jadavpur University, the intro ML course that is there, we have proved this is using moment generating function. This is in your GATE syllabus. If you want, go back and study this. Moment generating functions. That the sum of normal distributions is also normal. So what I'm trying to say is, what you have to estimate the parameters of Qn. What is Qn distributed as? Mu and sigma, if I ask you. Question mark, question mark. So first, mu. What is the expected value? So expected value of Qn is the question. Is equal to expected value of summation of Ri I equal to 1 to n. These are all zeros. This is equal to 0. Yes or no by linearity of expectation? Do you agree? Fine. Okay. Second, what is the standard deviation or variance of Qn? What is the variance of Qn? Again, for uncorrelated or independent events, we saw that the variance is the sum of individual summation of 1 by n, and constants go out as squared, which is equal to, these are all 1. So this is n into 1. So variance of Qn is equal to 1 by n. So what is the distribution of Qn? Normal, 0, 1 by n. Yes or no? Now, what does this remind you of? Do you remember this? This n goes to 0 as n tends to infinity, which is again law of large numbers. But fine. So why am I trying to do this? I'm trying to find a bound to get this equation that I have over here. Is the derivation of the distribution of cube clear to everybody? So I will try to get the bound. So I'll prove that. So I'll try to prove. So let's go again to the end and then try to prove. Okay, let's prove this. So I said that Qn equal to 1 by n, summation of n equal to 1 to infinity, or n1 to n, sorry, Ri is distributed as normal 0, 1 by n. If Ri is distributed as normal 0, 1. Fine. So now my question to you is, what can I say? My question to you is the probability that Qn is greater than an epsilon. Why am I trying to find this? Any question, any hints or intuition behind trying to find this? So Qn has mean 0 and standard deviation 1 by n. Yes or no? This is how a Gaussian curve looks like. So the PDF of the Qn of x, as we had seen, is root 2 pi 1 by sigma e to the power minus x squared by 2 into 1 by n. Yes or no? This is the curve that we have of the Gaussian distribution. This is the bell curve. Fine. So if this is the bell curve, so what can we get from this? So I am trying to say that, is there any data? Say I select arbitrary epsilon. So let us try to get the intuition clear, at least if you have not done your homework. So again, sorry. So say this is your bell curve, and I select, say this is your epsilon. My question to you is, you say this is your epsilon. So the idea is to be in arbitrarily close. So epsilon tends to 0 region of 0, right? So because we are estimating Ri to be 0, that's what we want. We want Ri to be 0 and not 1 or 2. But due to the noise, we are getting some other terms. There's some lag in my tab screen. Okay, yeah. So we want Ri to be as close to 0 as possible. But due to some lag, what is ending up happening is due to some error, what is ending up happening is you are getting off by from 0 by some amount. So we can approximate them and we can get that using what is called as the Markov inequality. I have proved this again last time. You can go back and see it again, which says that the expected value of Qn by this. So this is upper bounded by the expected value of a function f of Qn by f of epsilon. right? So this term on the top over here is the function f has to be r to r plus and monotonically increasing. If these two conditions are satisfied, increasing, then any random variable can be upper bounded using the Markov inequality. I have shown Chebyshev's inequality and the Chernov's inequality, which we'll be using here. Say f of x is e to the power of tx is the assumption that I have. So what is your upper bound going to become now? Can you tell me? Un less than or greater than epsilon is going to become? What is it going to become? If e of tx is f of x is equal to e of tx, which is an increasing function, yes or no? From 0 to infinity, it's an increasing function. For t greater than 0, of course. Is it fine to everyone? What will be the upper bound if you're following? Is there anything wrong? You can tell me. Yes or no? E to the power, the expected value of e to the power tqn by e to the power t epsilon. Right? Okay, let's get it done. You're not following. So this is e to the power minus t epsilon and expected value of e to the power tqn. So now, how do we find the expected value of e to the power tqn? What is the expected value? Can you tell me? What will I use? What is the expected value of f of x? This is integral of f of x, or rather let me write g of x, the CDF dx, yes or no? The lotus, this is what we have proved in lotus. So this becomes, the integral becomes e to the power of tx, e to the power of minus t squared by 2 sigma squared dt. Sorry, x squared by 2 sigma squared dt by 2 pi sigma. So here I am assuming that Qn is distributed as normal 0 comma sigma squared. I will put sigma square equal to 1 by n at the end. Is this fine with everyone? I just use the lotus formula, and this is the function which expected value I want to find. Okay, so now let us try to find this. Any idea how do I compute this integral? Any idea? Okay, if there's no idea, let's try to simplify. Minus t square plus 2tx sigma squared by 2 sigma squared. Any hints now? I just did an LCM and multiplied the expected values, the exponentials. Any hint?
Complete the square.
Yes. So we'll complete the square. So you'll get minus x minus 2tx sigma square plus sigma squared t square, right? T square. That's right. By 2 sigma squared into e to the power of t squared sigma squared. Oh, sorry, not sigma squared. Sigma
That are like
4.
sigma to the power 4.
Yeah, 4. Sigma to the power 4, right? Is this fine?
Yes.
Yeah, okay. So now what will I end up getting? The integral is minus infinity to infinity e to the power of t square sigma square by 2 e to the power minus x minus what is it? Sigma to the sigma square t squared sigma squared t whole squared by 2 sigma squared by 2 pi sigma. Do you know the value of this integral? We have already done this. This is normal sigma square t sigma square. This is the distribution. What is the integral of our distribution out of PDF? This is the normal distribution, right? It is, we can clearly see this is the normal distribution. So this goes to 1, yes or no? Because the summation of fx of x dx from minus infinity to infinity is equal to 1 by law of total probability. Fine. So this becomes t squared sigma squared by 2. So now, what does the upper bound end up becoming? So your upper bound expected value of qn ends up becoming e to the power t square sigma square by 2 into e to the power minus t epsilon. Yes or no? Which is equal to sigma squared is already we have said is equal to 1 by n, which is equal to e to the power of t square by 2n minus epsilon minus t epsilon. Right? So this is your expected value. Or not expected value, sorry. The p of qn greater than epsilon. Now, can you tell me, is this a tied bound? Is this a tied bound? Can I remove some variables from here? Some variables are independent of the epsilon and the q's. Can you tell me? In this equation, one variable is independent of one variable. Rather, t is not dependent on n and epsilon, right? Yes or no? Therefore, it should be, do you agree? It should be true for all t. Yes or no? If it is for any t, it means it should be true for all t, correct? So which it means that it is still going to be less than the infimum or the minimum of minimum over t to the power t square by 2n minus t epsilon. Yes or no? The minimum value. So now tell me, what is the minimum value? How can I find? ddt e to the power of t square by 2n minus t epsilon. Just put it to 0. So you get 2t by 2n minus epsilon into the same constant e to the power t square by 2n minus t epsilon, which is again we can be cancelled because it is not 0, which says that t is equal to n epsilon. Fine. At t equal to n epsilon, this will be the infimum. You can take the second derivative and see as well, no problem. So this becomes the probability of qn greater than epsilon is becomes e to the power of n square epsilon square by 2n minus n square epsilon square. Just putting the values. So this becomes, or rather n epsilon square, sorry. So this becomes e to the power minus n epsilon square by 2. Yes or no? Any questions? We derived the main part of it. So you clearly see that as epsilon, what is the intuition here? As epsilon becomes large, say epsilon became very large, what will this become? This will become 0 or no? Yes or no? So that there is not much of a probability that it is going towards, it will be away from 0. Do you agree? Say n is tending to infinity. So what will you get? Qn greater than epsilon is less than 0, which means it is equal to 0 because probabilities cannot be 0, right? So which means that as n tends to infinity, for all epsilon, this is true. Right? So this is the dynamics between epsilon and n. As n increases, so what is the error you want? Say you want an error, 10% error. So you can choose an n so that this gives you 10%. Yes or no? Dynamics between, we'll do that between n and epsilon. Okay, fine. Let's try to put the value here. So this is the value we'll be using. Where is it? Yeah. So now for this process, I get qn greater than epsilon is upper bounded by minus n square or n epsilon square by 2. Yes or no? This is what we got. Let me just check. Yeah, that is fine. So now, what can I do? I want, say, this error term to be as small as delta, right? As small as delta. So just to avoid confusion, I will change the above delta in the NCB to not a different delta, which can be very small, a capital delta. So please tell me, please interact. Otherwise, it's becoming very monotonous for me. E to the power minus epsilon square by 2 is same as, we want to put this same as delta, which means that I want the error to be less than delta. Okay. So now let's take log on both sides. So if you take log, you get n epsilon square by 2 is equal to log delta. Is this becoming familiar now to the equation that we solved? 2 by n log of 1 by delta. So epsilon is root over of 2 by n log of 1 by delta. Okay. So 1 by delta is proportional to t, which is another proof in itself, but we're not going to go into that. So the idea is, as t tends to infinity, 1 by delta tends to 0. Or rather, delta tends to 0, sorry, as we have already seen. We have seen that as error, so this is as n tends to infinity, as n tends to infinity, no, we have already seen this, we don't need to prove. Delta will go to 0. We have already seen from this equation. So this numerator term can be substituted by n. That's the idea. So 1 by delta can be equal to n is the idea that I am trying to bring. Okay. So the epsilon becomes 2 by n log of n. Therefore, in terms of t, see, this is a constant term, so that you can take out, and other constants like here, since it's proportionality and so on, can be taken out as some constant c into log n or log t by nt of a. Is this proof clear to everyone? It says I derived the epsilon t, whatever you're trying to find out over here, is given by this term. So your q, so the probability of qn being greater than equal to c log t nt of a is equal to delta, or is less than equal to delta. So therefore, when we get this, we use this error, or the right hand side of the error, along with q. Where is the q function? To get the sampling, right? The number of times you visit a into inversely proportional to that into the log of t plus the q function. So okay, so this brings us to the end of Bandits algorithm. We'll do one more algorithm and then stop today. That's a smaller algorithm. Is this clear to everybody? This is called the upper confidence bound, because we have a bound over the error. We can choose a delta as we chose over here, and accordingly choose an n. So for every delta there exists an n. There exists an n t of a you have to sample. That is the idea. Okay. So now the last algorithm on action selection is known as the gradient based algorithm, which is also very similar to what things that we have done in machine learning. So I'll introduce all of these one by one, but it is not very difficult to understand. It's just a few lines of equation. Let's try to understand that. Say, so Okay, so let us try to have an intuition first. So what is the goal? Goal of RL. Again, recall the goal of RL. What is the goal of RL? Anyone? The goal of RL is to maximize.
Long-term.
Yes, maximize the long-term reward or the total expected reward. So do you agree? This the goal is expected reward you want to maximize. So there, this is the loss. You want to maximize L. Yes or no? Right? So here I'm trying to say is, how do you do that? So say the loss is a function of some parameters H, right? I will show you that the H's can be learned as this equation. If you want to maximize, it can be learned as the loss. This is called gradient-based optimization or gradient ascent here, because we are increasing. We'll see what it means. But before that, let us try to understand what is gradient ascent or what is gradient descent. Say you have a function. Let's try to visualize this. So you have a function like this. You start from here. If I just put a force along put a ball here, just put a ball, place a ball, at this location, what will happen? The gravity will pull it down, yes or no? So this will come to, unless it comes to the equilibrium, it will be pulled down, correct? The ball will come down. This exact idea was used by Newton to come up with gradient descent algorithm. So the idea is, along this gradient, that is the derivative of a function, say a loss function, partial derivatives if required, if there are multiple directions. If you go along the derivative, is the answer. So you can update thetas as dl, whatever your loss is, with respect to the parameters. So let us try to see this once again. So for a 1D case, say you started at xt, right? For this xt, when you start, you take a gradient step. Say at this point is f dash of xt. You take this gradient step and you say that I update my xt plus 1. This is my xt plus 1 as xt plus some, or rather minus some alpha into df dx, right? So whatever is the direction of the gradient or the derivative and gradient I'm using interchangeably, you try to go in the opposite direction, right? Here the direction of the derivative is positive because it's an increasing function. So I go in the opposite direction. I use the energy of this curve to go down into the equilibrium position. So let us see why is this true. So say I did it in one of the orientations, first year orientations last time. So say your function that you want to optimize, again, let me write it down. Theta star is argmin of theta, L of theta. I am telling you that theta t plus 1, if you update as theta t minus eta some learning rate. This is the learning rate again. dl d theta. Then as t tends to infinity, theta converges to theta star. That is a local optima. You can't really go to a global optima because if this graph is something like this, you will reach this point and stay there forever. That's the idea. You can never go to the global optima, but yeah, fine. Please ask questions if you have any doubts. So I'm telling you, say loss of theta t plus 1, we want to be less than the loss at theta t, right? This is all we want. We want to a decreasing sequence. We want the loss to decrease or not, right? Can I say that your update? So I say theta t plus 1 is some theta t plus some eta into some direction. This is a gradient or a direction. Okay, for our case, it's just a scalar if it is a linear, if it is a scalar setting. So now, can you tell me the Taylor expansion of this? L theta t plus 1 is equal to L of theta t plus eta gt. Can you tell me the Taylor expansion of the right hand side? Across
L of theta t plus
Okay.
eta gt into L dash theta t
plus
plus
ordered t theta square terms, theta t terms, right? Or rather eta squared g greater than eta squared gt squared terms. These are all can be ignored by the same Newtonian logic as we ignore in Euler equations. So what do you see? You see that L theta t plus 1 minus L theta t is equal to eta gt L dash of t, right? So now the question is, if this is less than 0, that's all we want to find, which implies L theta t plus 1 minus L of theta t less than 0, which means that gt L dash of theta t is equal to 0. So gt can be selected as the best model, the fastest descent, as L dash of theta t, the fastest descent. So therefore, the gradient descent algorithm says that eta t delta L delta t. Fine with everybody? Delta theta at theta equal to theta t. This is the gradient descent algorithm until convergence. Fine with everyone? Any doubts, any queries?
No, it's okay.
Okay. Fine. So now we want to maximize the function. What will you be? So this is minimization. So now in our question, what is our question? Our question is, our function is L theta, or L is expected reward, right? Our parameters are say H. So what if you want to maximize this? Maximize L of H, what will you do? Can you tell me? How will I update H? I will update H as ht plus 1 in the opposite direction, right? So if your graph is something like this, I will try to move up unless I reach the optimal position. That's the idea. Plus eta d expected value of RT by dHt. Okay, fine. So let us try to find this equation. Now, what is all this? What is the expected value of RT is the question. So now, for finding expected value of RT, let's try to get a trick done. Say you have a Monte Carlo again the same bandits problem. You have 1, 2, 3, 4, and 5 actions. 1, 2, 3, 4, and 5. I say that an action is more probable to be selected if and only if some ht of a, the energy function is high. We define some ht of a to be high, right? So ht of a is a map from the action space to the real number line, right? So what I mean is, so for every action, I will be mapping, say 1, this is 5, this is 2, this is 3, and this is, say 0. So I will give them some real numbers, and I will say that if 5 is more, if number is high, I select this more often. More often. Is this clear? I hope this is clear, right? Fine. But what we want is, we want probabilities. So to get probabilities, we'll use what is called as a softmax function. So what we want is the probability of AT being selected to be TA, right? We want the distribution of ATs. That is, what is the multinomial, that is P1, P2, P5. What is the probability of selecting each action, right? Such that P1 plus P2 ... P5 is equal to 1. Yes or no? But these necessarily does not sum to 1, correct? And they can also be negative numbers. So any idea how can I make them positive and also make them sum to 1? Look at this trick. So this is ht of a. Can I write? So I have told that an action is more probable of being selected if ht is high. So I am saying that at is proportional to h of t. And this has to be greater than 0, some function of h or t. Let us take some transformation t of h of t. Right, some transformation. So can you give me one transformation which will always make this positive?
Square root.
What? Square root is one answer. Another, but square is not monotonically increasing. X square is like this. It's not going to work. So we want a function that is proportional. It is proportional and also increasing. Exponential function will do. Good. So I want your function to be proportional to exponential is an option. So now I want also the sums to be 1. So what will I divide this by? So let's prove it. Let's have a proportionality constant k. So p1 plus p2 plus dot pk has to be 1. So tell me, e to the power of ht of all actions, summation of I equal to 1 to k, or rather, say there are b actions, 1 to b, k is equal to 1. Yes or no? Which means that k is equal to 1 by summation of. Yes or no? So I'll get. So this is how you derive. You say that the probability of at equal to a is e to the power of ht of a by summation of b equal to 1 to b e to the power of ht of b. So this is actually normalizing by the entire weight. This is normalizing by total weight. So do you agree this will sum to 1 and will be positive? Any questions? So this is called a softmax function, used a lot in machine learning. You can check last time's videos also if you are interested. Okay, so this is the softmax function. Fine. So now let us find out what is expected reward. Tell me, what is expected reward? How can I write this as? We have defined conditional expectation for this day itself. We don't know what is expected reward, but we know that what would be the reward if. What do we know? So say
The
this.
reward when action is equal to a.
Exactly, we know that. Remember this diagram. We know the reward functions things we know is expected reward given AT equal to A. This is known, but expected reward is not known. So what will I do? I will condition. So expected reward is, as who told me?
It's
This?
going to be the probability of choosing action A or times.
Good. So correct. So this is, say I define as pi of A or pi t of A. So this will be summation of RT, right? This is the, say your, what is this? This is the Q star function, whatever of A, right? This is how we define the Q function into pi of A. Yes or no? A equal to 1 to B. All the actions are selected. Any questions? So I will write this down again for your understanding. This is probability of AT is equal to A, right? And this is the expected value of RT given AT equal to A. So this is iterated expectation. Any doubts? Fine with everybody? Fine. So now what I all want to do is I want to take the derivative of this with respect to HT, right? This is all I want to do. If I can do that, my equation is done. A D D T H V. This is fine. But now I'll introduce one term over here and tell me if this is correct or wrong. I say that this is equal to A equal to 1 to B Q star of A minus some baseline R bar into DD of HT of A by T. Let us write HT for the time being, to not confuse with notations. Is this fine? Why is this correct? Can you tell me? These two are equal. I'm saying my claim is, proof is, see, the summation of R bar DDHT pi T of A is, do you agree? R bar DDHT summation of pi T of AI, sorry, I equal to A equal to 1 to B, whatever. What is this inner term going to be? These two are equal, right? Fine. The inner term is just 1, right? Because it's a probability, PMF. P1 plus P2 dot 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 PB is equal to 1. So the derivative of 1 is equal to 0. This is R bar into 0, that is 0. So that term does not contribute anything. We'll show why is that important later. But is this clear? Fine. Okay. So now let us write this equation again. HT of this is same as A equal to 1 to B. I will do one trick. Just be careful with the trick. Q star of A minus R bar pi T of A, and I will subdivide by pi T of A. Is this step valid? No problem with anyone? Okay. So now, again, do you see lotus here? Does this tell you this is expected value of A? Or rather, let's write this as AT is sampled from the pi distribution, pi T, and Q star of A minus R bar, say pi of A. Yes or no? Fine. So I'm telling that you sample AT from this distribution, which is pi, because this is the expectation that I'm getting. Yes or no? The summation I'm just writing in terms of an expectation. Do you have any question? Any doubts? And there's a slight mismatch of A's here. Sorry. Yeah. This was derivative with respect to an A. And since this is a bit of a, I will use B over here to avoid notational hazards. Okay. Do you agree with this? Not, this is has to be A. Fine. This is what I was referring to. There are a few A's over here. Let us not write A. Again, K. Let us write this as K. Fine. This is okay. Is this equation clear to everyone? I just multiplied and divided by the densities. Multiplied and divided by the distribution and took the expectation. Okay, so now this term becomes, so again this term I already know is expected value of RT given AT minus R bar, expected value of AT pi T right? Fine. So now what I say is, since there is iterated expectations again, I can take expectations out and write a single expectation across AT selected by pi T and reward selected as, can you tell me, distribution of AT equal to A? Yes or no? When you select an action A,
Yes.
you will get a, yes, good. So I will get RT minus RT bar pi T of AT by DHT. Please go back and look at the proof again. This similar proofs and algorithms will come up multiple times. You may have, I may give you in your assignment this to derive this, to implement this actually, because derivation is already done in class. Okay, so now this is actually done. Only this part is left. Can anyone help me to solve this part? So DHT of A e to the power of HT of AT by summation of T equal to, or say B equal to 1 to B e to the power of HTB. Right? So now let me help me with the derivative. Can you help me? The derivative is, so you take the numerator. You have two cases, right? If AT equal to A and if AT not equal to A. If AT equal to A, what will happen to the DHT of AT? E to the power of HT of AT. Can you tell me? So it'll just be e to the power of HT of AT, yes or no? Or rather capital A, whatever A you want, yes or no? If both are
Yes.
same. If they are not equal, what will happen? Tell me, it's a partial derivative. What will happen? Partial derivative is fix all other parameters or all other variables. So this becomes 0, right? It's the constant.
Yeah, this is 0.
Correct. So we can write this as the derivative of HT of A e to the power HT of AT as e to the power of HT of A into indicator that AT is equal to A. Yes or no? If it is equal, so this will be 1 if true, and this will be 0 if false. Okay. Now what will be this term? The derivative of the denominator, can you tell me? The derivative of the denominator will be just e to the power of ht of A. That's the only term, rest all of them will become 0, yes or no?
Yeah.
So now I can write this derivative as, by UV rule, e to the power ht of A, indicator of AT equal to A, minus e to the power of ht of A into e to the power of ht of AT, divided by b equal to 1 to b e to the power of ht of B whole square. So this becomes e to the power of, okay, I made a mistake, I think. Oh, this is the summation, sorry. So this term you didn't tell me is the summation, right? UV rule is the denominator is multiplied, yes or no? ht of A with ht of A, I will have a multiply product of b equal to 1 to b e to the power of ht of B, correct? That is uv dash or u dash v minus uv dash by v square is the derivative that I'm writing, if you remember. So now one of them will get to 0. So e to the power of ht of A by summation of b equal to 1 to b e to the power ht of B, indicator of AT equal to A, minus e to the power of ht of A by this summation into e to the power of ht of capital AT by the summation. So this becomes, what does it become? So this term is, again, pi t of A, yes or no? That's how we define pi t. Yes or no? Look at this equation. This is how pi t is defined as. So pi t of A, indicator of AT equal to A, minus pi t of AT. So I just put this equation back in the derivative, and I get this update rule that I have derived, which was written in this equation. Look at this. This is the equation that I will get. Okay, so now is that since the expectation is over 80, I can just write this as, what was the denominator that I had? So let us write this over here. So the expectation of RT minus R bar by pi t of AT into d by AT by dHT of A. So this turns out to be, so again, since indicator is there equal, so I can also replace this as AT, and I will get AT outside and A here. So both are same, they're equivalent. So I will get pi t of AT into indicator of AT equal to A minus pi t of, very nice, into R minus R bar. So now we get this equation. This equation turns out to be the gradient update rule. Update rule. I'll write it down. ht plus 1 of A is equal to ht of A plus some learning rate, expected value of RT minus R bar into the indicator of A equal to AT minus pi t of A. So now again, since it's an expectation, we showed, So this can be written as, so in a stochastic gradient descent, so it's stochastic means you do not take entire expectation, you just take, whenever there is an expectation, you can take one action and do the update. Plus RT minus T bar indicator. This is what you'll implement in your assignment. So what is the intuition behind this? At a particular time, you take an action and then update is for a current update. If they're equal, you update it by this difference. If they're not equal, just put the gradient or the selected action. Here, AT can be selected as epsilon greedy or UCB. So any questions? If there is no questions, I'll just run the code for UCB and we'll stop today. Please go over the derivation, the end part of it, because people had turned quiet. So we'll ask and ask me in the group if there is any doubt. Okay, I'll stop sharing from my tab and I'll share my screen. Okay. Can you see my screen?
Yes.
Yes.
Okay. So now, okay. So now, like, I'll use the same code as last time. So it's the same code as last time. And then the algorithm that I have just going to show you, the algorithm that I'm going to just show you is this UCB selection, right? I'll just keep it parallel so that you can check the UCB update. Wait. Just go back to the video last time. I explained the entire code in details in case you are wondering where this code came from. So look at this UCB action selection. I exactly wrote the same action selection that I proved in the class today on the right hand side of the screen. See QT plus C into log of 1 plus T, just to avoid log 0 terms, log of 1 plus NT, the number of times the current time, by NT. NT, as you may recall, NT of A is the number of times action A was selected. So when I do np.sum here in this equation, I am doing, so np.sum takes the sum over all the actions, thus total time. Okay, so then I just take the argmax of the UCB by the same way, and I select NT of A plus 1. So let's see, how does it work? This was the Bandits algorithm with epsilon greedy. And now let's see epsilon greedy. I have turned epsilon greedy to be false here, and I'm going to use the epsilon UCB action selection. Where is it? Here it is. See, look at this. Look at this here. The non-optimal hands were selected so many number of times. It was proportionally high. But as soon as I did UCB, see, everything just vanishes. This algorithm just very few times will it select the non-optimal hand, and it will converge exactly to the value as t goes to infinity. Do you see the beauty of a mathematically instituted or derived algorithm? This is the advantage of this. It just goes to 0, as I had proved in the theory. Again, let's try it for different values of C here. So I ran the code for different values of C. You can check the code, play around with it, and look at this. So when C is very high, it means that this second term initially will be very exploratory, because C is you're giving a lot of weightage to exploration. So that's why it converges slowly, but it never has noisy estimate. Its noise is little because you have explored for a long time and then converged. Similarly, the orange one is 1. it's a higher value, it's a lower value of the exploration. Therefore, you get more random samples and then converge. Much lower value, you get more random elements initially and then you converge. So this is how you can vary the weightage of the exploration step and see how the convergence is affected, with higher values of C giving a smoother but slower convergence. Okay, any question? There is none. I'll stop recording. Any questions? Anyone to ask for the class? Okay, I'll stop recording. Okay, anything you want to ask?